All right, welcome to The Explainer. Today we're going to tackle a classic physics puzzle, one you might have even wondered about yourself. If we've got Newton's second law, the famous F equals ma, then why do we even have his first law? I mean, it kind of seems like a leftover, right? A totally redundant rule. But as we're about to see, the first law has this secret, crucial job, a job that actually holds all of physics together.
So this is the heart of the problem. Something a lot of sharp students notice pretty quickly. It's really just a simple question of math. We all know the second law, force equals mass times acceleration. And it seems like it covers pretty much, well, everything.
So you really have to ask, what's the deal? If the mighty second law can explain what happens when there is a force and what happens when there isn't one, then what in the world is the first law even for? It feels like getting a special instruction that just says, breathe.
And you can see the problem laid out right here. I mean, look, on the left, you take the second law, you plug in F equals 0. What do you get? Well, A equals 0. No acceleration. Simple enough. But then, you look over at the first law. An object in motion stays in motion unless a force acts on it. Wait a minute. That's the same thing, just said with more words. They look completely identical.
But see, that confusion only pops up if we assume both laws are trying to do the same thing. What if they aren't? What if the first law isn't about calculating anything at all? What if its real job is to set the stage for the entire game of physics?
Yeah, this is a great way to think about it. It's like a sport. You have a rule book that defines the field, the boundaries, what counts as a play, and then you have the star player who actually runs around making all the moves. They're both essential, but they have totally different jobs.
The whole secret to this puzzle hinges on this one critical concept, the inertial frame of reference. Now that sounds fancy, but it's basically just any viewpoint or any coordinate system that's moving at a constant velocity. It's not speeding up, it's not slowing down, and it's not turning. Think of it as the perfectly stable ground where the rules of physics work just like you'd expect.
Exactly. The first law isn't an actor in the play. Its job is to build the stage. It's the law that essentially says, hey you, for F equals ma to make any sense, you have to be watching the show from one of these special non-accelerating seats.
Okay, let's put this to the test. Let's run a little thought experiment, because this is where the first law stops being some abstract rule and turns into a tool that we can actually use. Let's see if we can spot it in action.
So picture this. You're sitting on an airplane. It's on the runway, and the pilot hits the throttle. The plane is accelerating, pushing you back in your seat. Now imagine someone at the front of the aisle just lets go of a water bottle.
From your seat, inside that accelerating plane, what do you see? The plane is surging forward, and that bottle, what does it look like it's doing?
Right. From your point of view, it looks like that bottle just took off and flew towards the back of the plane. It seems to accelerate all on its own, zipping down the aisle.
And here's the paradox, right? What force is pushing that bottle? I mean, there's no little rocket strap to it, nobody threw it, and yet it's moving. So from where you're sitting, you're seeing an acceleration with apparently zero force. F equals ma looks like it's just been broke.
This right here, this is the first law's big moment. It acts as our built-in reality check. The reason F equals ma seems to fail is because you, on the plane, are in a non-inertial accelerating frame of reference. The law isn't broken. You're just trying to apply it from the wrong kind of place.
So, in an inertial frame, say for someone watching from the ground, the laws work perfectly. They would just see the bottle hang in the air for a second while the plane accelerates out from under it. Simple. But inside the plane, that non-inertial frame, things get weird, and the laws seem to fail.
So this is the first law's real job. It's a test. It defines what an inertial frame is supposed to look like. And the moment you see something accelerate without a force, like that bottle on the plane, the first law is like a giant flashing sign that says, warning, you are in a non-inertial frame. The simple rules don't apply here.
So just like we said, one law sets the rules of the game by defining the playing field. That's the first law defining the inertial frame. And only then, on that field, can the second law get to work and actually play the game.
But this leads to a final, pretty mind-bending question. We've just established that to do physics right, you need this perfectly stable, non-accelerating viewpoint. So, where in the universe can we actually find one? Well, here's the crazy part.
Think about it. The Earth is spinning on its axis and it's orbiting the Sun, so it's accelerating. The Sun itself is whipping around the center of our galaxy, so it's accelerating. And the entire Milky Way is being pulled by gravity towards other galaxies in our local group. So it's accelerating too. Absolutely everything is accelerating.
And that leads to this just staggering conclusion. Technically speaking, there are 0 perfect, truly inertial frames of reference anywhere. Now, they're an incredibly useful idea, and for most things we do here on Earth, our planet is close enough to being one. But in a deep cosmic sense, they are a pure ideal, an invention.
And that leaves us with this really profound final thought. If Newton's first law is our rulebook for finding a place that doesn't actually exist anywhere in the universe, then what does that mean for the second law, for F equals ma? Are Newton's laws ever perfectly, fundamentally true? Or are they just an incredibly powerful, incredibly useful approximation of reality? And, well, that's a question that takes us right out of Newton's world and drops us on the doorstep of Einstein.